Okay, so we left off, we'd actually just finished watching the video on waves when we left off, but we left off with this slide here where we were talking about the properties of waves that are both in common with simple harmonic motion and some of the ones that are unique to waves, okay? That being things like amplitude, that would be in common with simple harmonic motion, okay? It's the maximum distance that, in this case, the medium will go from its undisturbed or equilibrium position, okay? Wavelength was something that's unique, obviously, only to waves, right? But the amount of time it takes one wave to go by would be called what? Period, same as simple harmonic motion. The number of waves that go by every second would be frequency, same as simple harmonic motion, okay? So there's lots of things that are similar, lots of things that are going to be a little bit unique just to waves. Okay, if I'm looking at this particular diagram here, how many waves are on it? 3.5. Yeah. Here's one wavelength. There's two wavelengths. There's three wavelengths, and this is another half of a cycle. Okay, 3.5 wavelengths. That's going to be something that's going to be important when we get to standing waves, for you to be able to look at a diagram of a standing wave pattern and go, oh, there's this many wavelengths on that string, spring, whatever it is that's oscillating. Okay, be able to identify that very quickly. Okay, so that's good. That's going to be something that we have to be able to do. If this is one cycle, okay, there are 3.5 cycles on that particular diagram. Okay. So amplitude, as we said before, okay, that's not a new term, but when it's applied to waves, it's the maximum excursion of a particle in the medium. Okay, how far it will go from the resting position. Okay, so that's, like we said, something that's still the same. This is one full oscillation. Okay, would this, so we've got, this is one full oscillation, this is one full oscillation, this would also be one full oscillation, yes? How many times does a wave pass through equilibrium during a cycle? Twice. Okay, so if I start here, right, I go through equilibrium once, twice, back to here in a full cycle. And if I go from here, once, twice in a full cycle. If I start from here, once, twice. I don't count this one because that's where I started. Okay, everybody all right with that? All right, so wavelength, like we said, is represented by this symbol. This is lambda. Okay, it's the Greek letter L. Right? It's wavelength is going to be measured in meters. Okay, for pretty much everything. Even waves that have an incredibly small wavelength are still going to have their wavelength measured in meters, like light waves. Okay. Light waves have wavelengths that are like 10 to the -7 meters. Okay? Very, very short wavelengths. Right? And then sound waves can have wavelengths that are, several meters in length, depending on their frequency. Okay, so wavelength, like we said, is the distance between any two successive troughs, crests, or any other equivalent points on the wave. Okay. All right, and then obviously the time for one cycle, still called period, number of cycles per second, still called frequency. Okay, and that's all in there just as a review. Okay, so the stuff that's in bold is just definitions, and you guys already know all of those terms. All right, now, if I have a wave going by, okay, there's a property of waves that we don't really associate with like simple harmonic motion very much. I mean, a mass on a spring, yeah, we can look at its velocity. Okay, but when we're talking about a wave, okay, yesterday we did we had the slinky on the floor, and we saw that the speed of the waves is controlled by what?
Material of the object.
Right, the material, the medium that the waves are traveling through. That controls the speed of the waves. If I change any properties of the medium, temperature, depth, density, whatever, okay, if I change any of those properties, I'm going to change the speed at which the waves can travel. Okay, and then that's going to change other things about them. Everybody okay with that? All right. So a wave can kind of be or a train can kind of be an analogy of a wave, because usually you don't have a single wave traveling along. Usually you have what's called a wave train, which is a series of waves traveling together. Okay, so the length of each car on the train would be analogous to the wavelength. The speed at which the train is traveling would be analogous to the speed of the waves. How long it takes one car to go by would then be the period, and the number of cars that go by every second, frequency. Okay, so kind of an analogy there, and I only bring that up because we kind of use like a train car analogy a few times throughout the unit. Okay, all right, how's everybody feeling about properties of waves and what waves are? Okay, so waves are a traveling disturbance, they carry energy, waves themselves are not matter, but they require matter to travel, except for light. Okay, things like that are important for us to remember. Okay, so waves in simple harmonic motion. Okay, so we got, if we have a mass on a spring and it's oscillating back and forth, okay, and this is the video, I couldn't find it, I don't know what happened to it, someone must have, maybe Mr. Dickey deleted it, okay, because we share the same folder, I don't know. But if we have a mass on a spring oscillating up and down, and I put like a marker or a pencil, or in the case of the video we had, a can of spray paint, okay, on that mass, and then I pull like a piece of paper past it while it's oscillating up and down, what shape will it draw? This shape, right here. Okay? That's how we know that simple harmonic motion and waves, okay, are kind of tied together. Simple harmonic motion is going to produce a sinusoidal wave pattern, okay, as it occurs. All right, so I think that's it for what we need from there. Okay, next thing I want to talk about is this. This is the universal wave equation. Okay, and in case you guys forgot, because I haven't, I did forget yesterday. Yesterday I was supposed to give you time to work on your simple harmonic motion assignment. And I taught waves instead because I'm old and forgetful. Okay? But I haven't forgotten that I did say I would give you some more class time to do that, and I'm going to, right after I talk about the universal wave equation. Okay? And then you'll get like the last, I don't know, 40, 45 minutes or so of class, okay, to work on that, because I promised that, and I want to honor that. Okay? So this is the universal wave equation. Okay? It allows us to calculate the speed of the waves if we know their frequency and their wavelength. Okay? We can also write it like this. Okay? On your formula sheet, it only appears in the first form. Okay? And that's because on your formula sheet, we have this formula. T equals 1 over F, which means F equals 1 over T. So if F is 1 over T, then V equals 1 over T times lambda, which is lambda over T. You guys follow the manipulation? Okay. All right. So when we do this, okay, this is going to be in meters. This is going to be in seconds. Okay, for this is going to be in hertz, which are cycles per second, and this is going to be in meters, so we're going to get meters per second, okay, no matter which way we do this. Okay? Now, the universal wave equation has an important implication for waves, okay? Because there's a property of waves, one property, that can never change once the wave is produced. Okay? So once a wave is produced, one of those three things can't change. Two of them can and have to, but the other will never change. Which property, speed, frequency, or wavelength, will not change once the wave is produced? Okay, think about this. You ever been at like a swimming pool where they're playing music, they're playing it above the water and below the water? Okay? Other than the fact that it sounds like it's underwater, can you still tell that it's the same song? Yeah. Well, the fact that you can tell it's the same song is because of the frequency. Okay? Underwater, sound travels way faster than it does in air, but it doesn't sound any different because its frequency never changes. So those same sound waves have the same frequency, but they have a greater speed and thus a greater wavelength. Okay? Because if speed changes and frequency can't change, that means wavelength has to change in the same way so that frequency doesn't change. Okay? This is actually something that can be a problem for synchronized swimmers. Okay, has anyone ever seen synchronized swimming? Okay. So sometimes you got people that are above the water and people that are below the water. If the speakers are a really long distance away in the air, but obviously they're right in the pool in the water, they can get out of sync and not be synchronized anymore, because the ones that are underwater hear the music before the ones that are above the water, if the speakers are really far away. So they generally try to, make sure the speakers are really close so there isn't a delay like that. Okay, because otherwise it would be really hard to synchronize your movements to the music, because the people above are hearing it later than the people below the water. Okay, so it could be a problem. Okay, so here's kind of how this would work as a real world example. Okay, out on Highway 2A, out where the lights are there by the GM dealership and the vet clinic and whatever out there, okay, by that first set of lights. The speed limit inexplicably changes from 100 to 60. Okay, I think it should be 80, but I guess I'm in the minority. Okay, so right here is where that speed limit changes from 100 to 60. Out here, where everyone is going 100, not 600. Okay, 60. Okay, out here, what are you told you're supposed to do when you're traveling faster? In terms of the car in front of you. Yeah, give it 2 seconds, right? You got to give good following space. Okay. Well, at 100 kilometers per hour, is that 2 seconds a bigger distance? It is. Okay. Now, here's what happens when these cars are approaching the line that says you have to go 60 now. Okay. This car gets to that line first. Yes. Okay. So it slows down. What happens to the distance between it and this car? It closes because this one hasn't had to slow down yet. Okay, so a little while later, these three cars look like this. They're now traveling slower. If I'm here and another person is here, we will both see 3 cars per second. But the distance between the cars and the speed at which the cars are traveling will be different. Just like waves, the frequency can't change, because when the speed changes, so does the wavelength. Okay? A wave would do exactly the same thing. Okay? When a series of 3 waves approaches a boundary where the speed is going to change, the first wave will enter that boundary or hit that boundary and enter a slower medium. It'll slow down and get shorter, and the waves behind it will get right up close to it before they get there, and then they'll shorten. Okay? And I'll still see the same number of waves every second. Okay? This is also why if I've got a red light, okay, and I'm in the pool, I'm looking at this red light, and then I go down below the water. When I'm in the water, the light still looks red, because the color of the light is dependent on its frequency. It doesn't change, it's still red. Okay, but the light travels slower in water than it does in air. Okay, actually significantly slower, but light's really fast, so you don't really notice it. Okay, everyone kind of follow me on that? Okay, so the universal wave equation kind of deals with this idea. Okay, it deals with the fact that speed and wavelength are properties of a wave that can change after the wave is produced. Okay, frequency can't. Once a wave is produced, its frequency will always remain the same. Okay, now can I change the frequency that a source produces? Absolutely. Okay, if I'm tuning a guitar and I pluck the string and it's like, ooh, that's not right, and I just crank on the tensioner, well, I changed the source. Every wave produced after I twist on the tensioner, okay, is going to have a different frequency. They're going to travel at the same speed as the first few waves because they're in air. Okay? But because I changed the source, I changed the frequency. Once a wave is produced, its frequency will never change. Nothing can be done to change its frequency once it's produced. Okay, everybody all right with that idea? Okay, so frequency of a wave can never change. I think I've said that now about 20 times. It's probably important. So then why does an ambulance sound different when it's approaching you than when it's going away? Yeah, Doppler effect. Okay? The sound you hear is because of the frequency. So I just said frequency can't change. How come the ambulance sounds different?
Is it because you get closer to the source?
It's a little bit. It's because the source is moving. Okay, and maybe the observer is moving as well. So it's producing waves. Those waves have the same frequency. There's nothing different about them. The frequency of the waves isn't changing, but the rate at which you pass them does. So if the ambulance is stationary and I'm moving towards it, I encounter the waves faster than I would if I was standing still, because both me and the waves are moving. Okay? When the ambulance is going away from you, it sounds different because as it produces a wave, it runs away from it. And it stretches it out. Okay? It's actually still producing the same frequency of waves, but because it's moving, we perceive them to be different. It's not that they've actually changed, just our perception of them.
When you say that like the ambulance is like, it's like running away from them, would the wavelength change?
The perceived wavelength would change, yes. The actual wavelength produced isn't changing. But because it's running away from it while it makes them, we perceive it to be. And same when they're coming towards us, right? When they're coming towards us, they produce a wave, and then they don't get as far away from it as they should, or they would if they were stationary, right? So then they appear tightened, and the frequency is higher.
Because you're moving faster.
Right,
Okay.
yeah, and you're going to encounter the waves faster than you would if both of you were stationary. Okay, that sort of makes sense? Okay, so that's why that happens. It's not that the frequency is actually changing, it's that our perception, or how quickly we encounter the waves, is changing. Okay? The waves still have the same frequency they would have had if it wasn't moving or we weren't moving.
So say there was like a hypothetical like siren in the air and you're traveling on an airplane. Because you're going like so much faster, would that have like a drastically different effect? Like say there was like a flying ambulance, like, so you know how when you're in a car, like you said you'd come like closer to the waves, like that, would that happen in an airplane with, like, would that be increased? Like, would
Yes.
it would just be like.
How fast you're going increases the Doppler shift.
Okay.
Okay, so if you're barely moving, the Doppler shift is imperceptible.
Okay.
Right, so if I'm walking towards an ambulance, it doesn't sound any different than when I'm standing still. But if I'm in a plane jetting towards the ambulance, it sounds a lot different.
Okay.
Okay, and in fact, that's what causes the sound barrier. Okay? Anyone ever been at an air show when the plane flies right over top? Okay, when a plane is going close to the speed of sound, it sounds like a high-pitched hiss. Okay, because what's happening is it's making lots of really big sound waves, very high amplitude, but it's moving at pretty much the same speed as the sound, so the sound can't run away. Right? So you're producing these waves, but you're moving just as fast as they are. Okay? And a sound wave is a compression and a rarefaction. So what happens is you get all these compressions of compressed air building up in front of the plane. Okay? That's why for a long time everyone thought you could never go faster than the speed of sound because of the sound barrier. Right? The sound barrier, that's why they called it that. Planes would run into the thing and blow up. Okay? Because this wall of incredibly dense air would build up in front of the plane and just break it. Okay? They had to figure out how to make kind of a tunnel in that wall of dense air that the planes were creating because of how fast they're going. Now, once you get through there, you get a what? Sonic boom, which is the release of all that pressure. Because you've got all this pressured air right in front of the plane, and once you break through, that pressure is very quickly released. Boom. Okay? All that pressure just goes away. Okay? Then the plane can just go. Because now suddenly all this air that was in front of it isn't there anymore. Okay? Now, if that plane's coming towards you and it's supersonic, what do you hear? Nothing. Yeah. Okay? Because it's going faster than the sound it's producing. So all the sound falls behind it. Okay? Now, once it's right over top of you, get flat on the ground, okay? Because it's gonna be real loud, real fast once it gets over top of you, okay? Because planes are really, really loud. Okay? If it's already broken the sound barrier, there's no boom to worry about. You only get the boom when you break it, okay? There isn't a boom that constantly follows it, unless you stay right at that speed, which sometimes they do. At air shows, sometimes they'll hold that, and you can actually see a cloud form in front of the plane. We'll talk about it when we talk about the Doppler effect, but that's kind of where all of that goes. Okay, is that making some sense? Okay. It's gonna get you an hour to work on your simple harmonic motion assignment. So, no excuses, it should be done after today then, because that'll be what, an hour and half, hour and 40 minutes we've had to work on it. Okay, all right, that's the plan.